Okay, let's get into inverse trigonometric functions. So when we're thinking about inverse functions, it's important to remember that inputs and outputs switch places, basically. So our original trig functions, the domain or inputs are going to be these angles that we're going to be plugging in, right? We input angles and we output some sort of ratio. But when we're talking about their inverse trig functions, inputs and outputs are switching places. So the domain or our inputs are going to be ratios, fractions, and then our outputs are going to be these angles or measures of angles. And these could be either in degrees or in radians, just depending on the problem. So if you see sine of pi over 6, that's plugging an angle into the original trig function. We're going to output a ratio. Well, that's going to be equivalent to saying that pi over 6 is equal to sine inverse of 1/2. Or another way to write this that you're going to see along the way that's equivalent is saying pi over 6 is equal to what we refer to as arcsine of 1/2. So when you see arcsine, that means the exact same as sine inverse. Same thing is true about arccosine and arctangent. All right, so when we're thinking about inverse functions, only one-to-one functions have inverses. So it's important to note as we take a look at these graphs of sine, cosine, and tangent, one-to-one functions have to pass the horizontal line test, meaning that if you draw any horizontal line going through your graph, it only hits the graph in one place. So what we have to do is we have to limit our domains for these functions. So we're going to cut down the domain of sine instead of it being this periodic function that, kind of oscillates in between +1 and -1. What we have to do is we have to cut down that domain from -pi/2 to +pi/2. That way it passes the horizontal line test and it's going to be a one-to-one function. So for sine, it goes from -pi/2 to +pi/2. For tangent, it also gets limited between -pi/2 and +pi/2. So these two are very, very similar. We include these endpoints at -pi/2 and pi/2 here for sine inverse, whereas we don't include them for tangent because these are where our vertical asymptotes are going to be located. Now, cosine is kind of the outlier just based on its graph, that we still want it to go in between 1 and -1 as far as these y values go. But for it to be 1-to-1, we don't keep it between -pi/2 and +pi/2 just based on what its graph looks like. Instead, it's kind of weird that it goes from 0 to pi. So we have to be a little bit careful about cosine and its inverse. Just based on the graph, it's going to be limited between 0 and pi as opposed to this -pi/2 and +pi/2 that we see with sine and tangent. So let's rewrite just a couple of these real quickly. So we're going to be looking at sine of 5pi/12 is approximately 0.96593. Let's rewrite this using into a relation involving an inverse sine. So basically what we do in this situation is we are going to apply a sine inverse on each side. So sine inverse of sine of 5pi/12 is approximately sine inverse, just doing the same thing to both sides of our equation here. And you don't have to show this work after you're comfortable with rewriting this, but basically I've applied a sine inverse, this function on each side. On the left-hand side, we're going to get this nice canceling out that sine inverse and sine are inverses of one another. So we're going to get some canceling out and get 5pi/12. And that's an acceptable value because it's between -pi/2 and +pi/2. 5/12 is smaller than 1/2. And on the right-hand side, we can just say sine inverse of this decimal 0.96593. It's a weird looking 9, but go with it. On this bottom one, we can rewrite this instead of cosine of 1/2 is approximately 0.8776. To write that with an inverse cosine, we can say, well, 0.5 is going to be approximately cosine inverse or arccosine of 0.8776. And there you have it. All right, hope this helps out on kind of understanding why we cut down the domains where we do. All right, good luck.